Here's a solubility question where they're giving us the solubility for each of the salts directly. So this is actually the easier type of solubility or KSP problems. Importantly, solubility is the value of X in the ice table. So if they're giving us solubility, they're giving us the value of X straight off. Let's start with part A. First, notice that we've got lead 2 phosphate. Let's start by writing a good dissociation equation. You do have to know your polyatomic ions. And if you need to brush up on those, go ahead and do that. That's a good. At this point, we should know those. And actually, in part B, we'll see kind of an obscure one. Okay, so we've got a little dissociation equation. If we make an ice table, solids will drop out, and we can safely presume that there's none of the ions that comprise the solid salt initially present. So we would shift to the side with the zeros. So plus 3x and plus 2x. Notice that the coefficient value has to match the number in front of x. So 2 means plus 2x and so forth. Okay, so then at equilibrium we have 2x for the phosphate and 3x as the expression for the concentration of lead 2 ions. Now from that we can write a value or expression for KSP. So thinking back to chapter 13, it's products over reactants, all raised to the power of their coefficients. And remember that you get to ignore solids. So yes, we do have a reactant, but that reactant is a solid, so it does not belong in the ice table. And then it's as simple as plugging in the values that we've obtained. So in our ice table we had 3x for the lead ion and 2x for the phosphate ion. So 3x quantity squared times 2x quantity squared. Don't lose the exponent nor the coefficient. So when we crunch these numbers, let's see, 3x quantity cubed is 27x cubed, and 2x quantity squared would be 4x squared. If you multiply that out, it's 108x to the 5th power. Okay, now for the part of the problem that is really the take-home message here. If they're giving us solubility directly, and they said in part A, the solubility of lead 2 phosphate is 6.2 times 10 to the negative 12th, then that is the value of X. So where we see X in this expression, let's write in 6.2 times 10 to the negative 12th. All of that raised to the 5th power. This involves some crunching with the calculator, but once that's complete, we arrive at a really small number, 9.9 times 10 to the negative 55th power. Ooh, that's small. Next question, part B. They're asking us to consider calcium oxalate. That's an interesting salt. And we need to write a nice dissociation equation to begin with. Well, one thing, you definitely have to know your polyatomic ions. So C2O4 might not be the most common polyatomic ion that you come across, but it is an important one, and it's going to affect how we handle this problem. So oxalate ion is C2O4, all carrying a 2 minus charge. If it's paired with calcium, it's actually combining in a 1-to-1 ratio in the salt. So this equation is balanced as written. 1 calcium ion and 1 oxalate for every calcium oxalate salt. Let's write an ice table to go along with this. Solids drop out, of course. You can safely presume 0 for the initial concentration of each of the ions. And this ice table will be easier than the last one. It's only X and X. The coefficient for both of those ions is a 1. So if we write the expression for KSP, KSP would be the concentration of calcium at equilibrium times the concentration of oxalate. And since those values are both X, it's X times X, or X squared. And once again, solubility is the value of X, and they gave us that value directly in the initial question. In my case, the red number was 4.8 times 10 to the negative fifth. So to complete this one, I just need to take that number, 4.8, 10 to the negative fifth, that they had initially given us, and square it. So I'd pull out my calculator, punch that in, and I arrive at 2.3 times 10 to the negative ninth. And that's the answer. That would be the numerical value for KSP for this salt. And all we had to do was plug in the value of X that they gave us, which they call solubility. But in order to get the expression written right, we needed to give a good dissociation equation and flesh out the ice table.